Okay, so let's get started. All right, last time we introduced two very simple, the simplest chaotic systems, really, a sawtooth map and a Baker's map. The sawtooth map is the simplest in the sense that it has only one dimension, right? And it has a Lyapunov exponent exactly equal to 2. So if you have a small perturbation, every time, every map, every iteration, the small perturbation gets amplified by a factor of 2, okay? The Baker's map is really exactly the same as the sawtooth map, but added with a stable component. So the sawtooth map is a good example if we only want to look at what happens with the unstable directions. And the Baker's map is an excellent simplest test case for us to understand the interaction between a stable and a unstable component in which happens in any chaotic systems.
So I have a question.
Yes.
So it's a mapping, right?
Yes.
So we can, for example, map the trajectory of Lorentz system in the big map, right?
Baker's map, yeah. Yeah, so it's a map, and we can it's really a simplification of a continuous dynamical system, just like we simplified the continuous time van der Waals oscillator or a periodic system into a periodic map, right? That has this negative slope. That basically it's a if we take a Poincare section of a periodic oscillator, we can easily get a map that actually behaves periodically. So similar in a chaotic system, when we take a Poincare section of a chaotic system, we get a chaotic map, right? So, and the Poincare section basically helps you remove the neutrally stable component, which is the time evolution direction, right? We know, like from the periodic oscillations, if you perturb in the direction of du dt, that perturbation is neutrally stable. So taking the Poincare section removes that part and converts the continuous ODE into a map, right? So that's why we are focused on map right now. And once we understand what happens on the unstable direction, and then once we understand the interaction between the unstable and stable directions, then we can add in the neutrally stable direction by switching from maps to differential equations. So that's kind of the strategy we are taking in understanding chaotic systems in this class. Okay. All right. So today we're going to continue looking at the sawtooth map and the Baker's map, which is going to help us understand what happens on the unstable direction and the interaction between stable and unstable directions. So first of all, let's keep focus on the Baker's map. So last lecture we have looked at a simulation of a Baker's map, right? That gives us a fractal structure on the unstable direction. Okay, so today, to begin with, let us actually use a little bit more numerical analysis, a numerical test to more zoom into what is happening on the stable direction, right? So here we are trying to get really the dimension of the Baker's map. So what do we mean by dimension? So let me first introduce like a generalized understanding of what dimension is. We all know that a line or a curve is 1D, right? An area, right, in a two-dimensional plane is 2D. And a solid that has a volume is 3D, right? So there is mathematically, there is a more rigorous way of understanding what is 1D, what is 2D, right? That actually goes beyond a integer dimension. So the dimension can be defined as just like many things in math, defined as a limit of limit as an epsilon goes to 0. The logarithm of n epsilon times the logarithm of epsilon. So let me, the only thing I want to make sure is what is n epsilon. Okay, so n epsilon is the minimum number of balls you have to use to cover that geometry where the diameter of the ball is epsilon. All right, so for example, if this is my epsilon, right, if this is the diameter of the ball is epsilon, then in this one-dimensional case, I need, if I want the minimum number of balls that covers this one-dimensional line, I need something like that, right? I need to basically chain a series of these to cover this line. And it's intuitive that if I reduce my epsilon by a factor of 2, I need to increase the number of these, right, by a factor of 2. So every time epsilon gets reduced by a factor of 2, n epsilon gets increased by a factor of 2, right? So now if you think about what happens to the logarithm, right, every time epsilon gets reduced by a factor of 2, which means the logarithm gets reduced by a constant factor, then this n epsilon gets increased by the same constant factor. So what is the limit? Right? The limit, if as this part reduces, this part increases, yeah. So essentially, what we get is 1 second. The logarithm. Actually, sorry, the other way. It's actually the ratio of these, and I need the minus sign. So it's the ratio of the logarithm of n divided by the logarithm of epsilon. Okay, so basically every time epsilon gets decreased by a log of epsilon gets decreased by a constant factor, which makes the log of epsilon goes to minus infinity, right? The log of n epsilon gets increased by the same constant factor, which makes log of n epsilon goes to plus infinity, right? So essentially, if I draw a plot of the log of epsilon, no matter where it starts, right, it goes to minus infinity. So this is actually let me draw the log of epsilon as the log versus log of n epsilon, right? So log of epsilon, let me actually put a minus sign here because log of epsilon goes to minus infinity. So what happens is that when epsilon gets increased by a factor of 2, whenever epsilon gets decreased by a factor of 2, minus log of epsilon gets increased by log of 2, right? And in the one-dimensional case, n epsilon gets increased by the same factor, a factor of 2. So n epsilon, log of n epsilon gets increased by the same delta, right? So the slope is going to be 1. As epsilon goes to 0, minus log of epsilon goes to infinity. So as this goes to infinity, the ratio is going to converge to 1.
So as the size of epsilon reduces, the size of ball reduces, the n increases, but it's like a linear relation with the slope of.
It's a linear relation with the slope of 1, right? So now contrast this with the two-dimensional case. If I have a two-dimensional area, right, and I have a ball of epsilon, it's easy to conceive that I need how many balls to cover the same area? I need actually on the order of 1 over epsilon squared many balls to cover the area, right? So in this case, my n epsilon is on the order of 1 over epsilon squared. So what does that mean? That means as my epsilon reduces by a factor of 2, right, my minus log of epsilon gets incremented by the same factor of, let's say, log 2, right? My n epsilon gets increased by a factor of 4 as opposed to a factor of 2. So in this case, my log of ne has to increase by log of 4 as opposed to log of 2. So the slope in the two-dimensional case is going to be 2 as opposed to 1 in the one-dimensional case. So this slope of how does log of ne increase as minus log of e increases or log of epsilon decreases, is actually going to determine the dimension of the system. Okay, you can easily think about in 3D, right? The number of balls I have to cover is proportional to 1 over epsilon cubed, right? As a result, the line is going to have a slope of 3. All right, so what really happens when we have a dimension that's not an integer? Okay, so let me first say like a 0-dimension object. What is a 0-dimension object? A 0-dimension object is as epsilon goes to 0, right? The number of balls I have to use to cover doesn't increase at all, so I have a flat line. That would be a 0-dimension. A point would be a 0-dimension. A collection of points is also 0-dimension, right? Because I have this fixed number of balls I can use to cover these collection of points. So let's take a look at what happens. What is really an object that has a dimension between 0 and 1? So that is really what happens to this set. So let's do something computationally, and you are going to see that using the definition of the dimension to compute the dimension actually is going to be a very computationally expensive task, because I would be so every time, right, you move in the x-axis for finite number, you are increasing epsilon, right, by a multiplicative factor. So really, in order to have a line that you can measure the slope, you have to make epsilon really, really small, right? What? Yeah. So basically, I'll show you, like in 1-dimensional, it's actually pretty doable, and we'll see how to do that. So what I'm going to do is I'm going to basically take the same map as we looked at the last time when a is equal to 3. So the amount of contraction in the stable direction is a factor of 3. Okay, and now instead of using NumPy, I'm actually going to import PyTorch. So the reason I'm using PyTorch is I want to do this actually in GPU. So that's going to do things a lot faster when you want to simulate a lot of points. So let's just make it let's just make 10 million initial trajectories. Okay, and we'll randomize it. So we will not be able to record the history because that will be too much data. So basically, we'll do, let's say, 100 simulations to 100 iterations to kind of initialize, to get rid of the initial transient, and then we'll start to do collect a histogram. Okay, so basically, the aim is to compute a histogram like what we are doing here, but we are going to be averaging not only over these 10 million samples, but also we are going to be collecting histogram. We're going to be averaging over time. All right, so that's kind of using the ergodic property that you can averaging time is the same as averaging in the ensemble, right? So why don't we average both in ensemble and in time so that we can get as much data as we can? Okay, so we are going to have a histogram. So okay, so let me actually instead of so that we don't get confusing. Okay, the xy would be numpy.random.rand, and let's make it torch.tensor. Let's actually make sure set default precision d type, right? So let's, because PyTorch defaults to 32-bit floating point, let's make it a bit more precise. Okay, so we'll initialize this and make it put it into GPU, and I think I've changed this to, yeah, I've already changed this to GPU. So let's just the CUDA simply makes sure that the data goes into the GPU for us to be able to run things in GPU. And let's initialize the histogram. Basically, histogram actually stores how many of these points lies within a particular interval, and let's only do it in the y direction. And let's make 10 to the 14 bings. So we'll really collect over a lot of bings, and we'll see that this many bings is going to allow us to really look at the dimension, okay, of the fractal object in higher precision. So this is a 10 to the minus 14. No, 2 to the minus 14 is the smallest epsilon we will be able to look at, right? So we'll basically look at all of these bings and say how many of these bings are non-empty, right? Okay, non-empty means non-empty means that there are points, right, within that bing, which means I need that ball to be able to cover that fractal object, which is going to be like the collection of points for which a long-time trajectory of this map is going to visit. All right, okay, so that's my histogram, and after these 100 iterations, I'm going to be doing 1,000 iterations, and my let's make it into GPU. The histogram is going to be plus equal to torch.histogram. I'm going to be using the y direction, and I need a 10 to the 14 number of bings, and from 0 to 2 is my the range. Okay, so let's just get rid of this for now and make sure this actually runs. Still initializing. Okay, so basically, if this is able to run successfully, what I'm gonna get is a histogram of 1,000 time steps, each with a 10 million numbers. Oh, zeros. Sorry. Oh, pi is not defined, so because numpy.pi. Yeah, remember the y-axis lies between 0 and 2, right? If the previous y is between 0 and 2, the next y, if you look at the definition of the map, is surely going to lie between 0 and 2. All right, so that finished the running, and if you have time, you can really make a much longer trajectory or a lot more initial conditions and make it run for hours, and you can get really refine the data out of this. What we are going to be doing is then let's actually first visualize. Actually, space between 0 and 2 and the 10 to the 14 and histogram, and let's make the not used to having to type numpy. Okay, numpy array again is no. Okay, so let's say h is histogram dot numpy. Actually, why do I have a star over here? Yeah, have to move it to CPU and then convert to numpy. Okay, so that is what we got, right? We basically have a you can see most of the bins are 0, right? But we do have still quite a lot of bins. Remember, like we have 10 to the 14, which is what, about 16,000 bins between 0 and 2, right? So there is a lot of points. But what is critical is how many of them are non-zero. So let's look at the number of h greater than 0 dot sum. So let's print this. Actually, just to print out. Well, let me actually do this here, and I'm going to be putting it in the next one. So how many of them? So it turns out about only 800 of them, 888 of them are non-zero. So remember, like there are a lot of h, right? And then let's actually combine every two of them. Okay, so basically h dot reshape -1 and 2. So basically make the second dimension 2. I'm really combining every adjacent two points. So that is making a bigger epsilon, a bigger ball, right? Dot sum over the first axis. So that is if I combine every two adjacent one of them and into a bigger ball, how many of these balls do I need to cover the whole space? So that turns out to be something, okay, the number of balls, if I have a one-dimensional object, right, then you would expect that the number of non-zero intervals would half if I double the size. But this actually did not exactly half. If I have a zero-dimensional object, the number of balls would be the same. If I have a one-dimensional object, it would half. I didn't half. It didn't also, it didn't also stay the same. Actually, let me I think 10 to the 14 might still be a little bit small. Let's make it 10 to the 16. See if I could get something. Actually 16, sorry. Let's stop these. Right. So what I'm going to be doing is so this right. So what I'm going to be doing is I'm going to say, okay, I goes from 1 all the way to 16, so 17. Okay, and the size of the ball is going to be exponentially larger and larger, right? And n is also going to be increasingly smaller as I make the ball size larger. So ball size dot append. So 2 is the whole width of the domain divided by h dot size, right? So that's the smallest ball size times 2 to the, actually goes from 0, right, to 17, 2 to 16, 2 to the I. So that is the size of the ball. And non-zero balls is going to be equal to that. So it's going to be reshaped with 2 to the I dot sum 1 greater than 0. Right? Does it make sense what I'm doing?
So for the reshape, it's not going to be like I. If it's 2D, it's 2 or 3D.
Yeah. So what I'm doing is that I'm reshaping H, which is the histogram, into a smaller number of bins. And the second dimension is the dimension that is adjacent bins in the final histogram, right? So basically what I'm doing is I'm getting a coarser histogram where the factor by which I'm coarsening is 2 to the I, right? If I is equal to 0, I'm not coarsening because the second dimension is 1. If I is equal to 1, I am combining every 2 adjacent ones. If I is equal to 2, I'm combining every 4 adjacent ones. Okay, finally, I'm going to say pylab.log. The x-axis is minus log, well, yeah, so I'm just going to say ball size and n. and let's take a look at what the plot is like. Okay, and let's pylab.read so that we can have a good all right. So the slope of that, actually the negative of the slope of that is going to be the dimension. All right. So you remember, like our definition of dimension is the limit, right? A limit of epsilon goes to 0, which means you want to look at the slope towards the very left, right? What happens here doesn't really matter, okay? And if you look at the slope, what is it? So for every, let's just look over here, right? So for every 2 orders of magnitude in decrease of the x-axis, we get the increment of roughly from here to here, right? So if you look at this width over 2 orders of magnitude, what is it? It's actually less than 1, right? Because the slope, I mean, if for 1, you would have a slope that goes like that, right? It's also greater than half, because for half, you would have a slope that goes from here to here. So this is a dimension slightly more than, yeah, a bit like 0.6. All right. So let's actually analyze it analytically to see what actually should the dimension be. Okay, so this is plotting things numerically, and now let's actually follow the definition and think about what the set actually is, right? Remember, like we have a set in the y dimension. That is, if we map the entire domain from 0 to 2, map it once, what we get is a set that it depends on what axis, right? This whole set of y is going to be either mapped to the first third of the domain or the last third of the domain, right? And then after second map, again depending on what axis, this part is either mapped to here and this part is either mapped to here, or these two sets are mapped to here and here. And after a third map, basically for every time, we are shrinking the existing set, right? Whether it's a whole contiguous set, or it's a 2 separated pieces or 4 separated pieces or whatever, we shrink by a factor of 3 and put it here. And if x is a different value, we are going to be shrinking it by a factor of 3 and put it over here, right? So basically what we have is in the stable direction, what we have is really a shrinking and duplication. The shrinking, the rate at which we are shrinking the stable axis depend on A, right? How much we shrink, in this case factor of 3. And how many copies we are duplicating the structure depends on the unstable direction, right? In this case, it's 2, right? We're duplicating this into 2 parts. Okay, so what we have ultimately is going to be finer and finer structures, right? And in this particular case, the structures can be easily understood if we take epsilon is equal to a series of balls with 2/3, 2/9, 2/27, etc. Because the width of this is 2/3, right? The width of this is 2/9, and once you map it further, you have either finer structures and you would get 2/27, etc. Okay, so when epsilon is equal to this, what is n, how many balls you would need to cover the whole set? Well, when epsilon is 2 over 3, you need exactly 2, right? And when epsilon is 2 over 9, you need how many? 4, right? And when epsilon is 2 over 27, you need another doubling, right? 8. So what happens here? What happens is that the balls, the size at which you can shrink the ball is equal to the rate of shrinking in the stable direction. And the number of balls, the increment in the number of balls you have to use to cover, right? In this case, it's a duplication by a factor of 2. It's doubled. That corresponds to how fast you are expanding in the unstable direction. Okay, so overall, if you now plug it into the formula, right? Basically, we have a limit of, let's say, you take this 2 over 3 to the power of I, right? This is then 2 to the power of I plus 1, right? So this is n, this is epsilon. There is a one-to-one correspondence. Actually, no, this is actually just I, not I plus 1. Okay, and so we have a limit of I goes to infinity, equivalent of epsilon goes to 0, right? Minus log of epsilon, which is 2 over 3 to the I, divided by log of 2 to the I. Okay, what do we get? As you take the limit of I goes to infinity, the 2 here just serves as a constant, right? In the numerator, it doesn't matter. So what we really get is a limit of, on the numerator, it's I times log 3. There is a minus sign which cancels with the minus sign here, and I times log 2. Okay, so that's actually log 3 over log 2. Okay, so how big is it? How big is log 3 over log 2? Pi dot log 3. Yeah, that's did I make a mistake in something? Why do I get a dimension greater than? So I actually flipped over. I flipped over the n and epsilon. So by the definition, the n should be in the denominator and the epsilon should be in the n should be in the numerator, epsilon should be in the denominator. So this is log of 2 to the I, log of 2 over 3 to the I, and so here we have log of 2 over log of 3. Yeah. So 0.63. That's the theoretical dimension, right, of the Cantor set, and that's should be the slope of this line we numerically computed. All right.
So it was like not exactly one. I cannot understand, for example, 0.36 dimension for the dimension. Right? We don't have it in physical space. Right?
We
But if we map it to a different space, maybe we can make this kind of non-digit space, which makes sense.
Yeah, so here's a way I think about this particular set, right? So remember, we have looked at the sawtooth map in terms of binary digit numbers. The way I can think about the Cantor set conceptually is to think about a representing a number in terms of not with the base 10, not with base 2, but with base 3. Okay, so you can have point 0, 2, 0, 0, 1, 2, or something like that. You can have a representation like that, base 3, right? Numbers. But if you exclude from all possible numbers represented in base 3, and you don't allow the digit 1 to appear anywhere, right, in this base 3 representation, you get this set. Okay, so what do I mean by not allowing the digit 1? This whole region, right, if you use a base 3 representation, the whole region between what I mean is really, let's say, instead of looking at the domain from 0 to 2, let's look at the domain from 0 to 1, right? 0 to 1. The whole region that lies between 1/3 and 2/3 is the number 0.1 something, right? So if you not allow the number 1 to appear, then this region is going to be excluded. All right, and then this region is 0.01 something, while this region is 0.21 something. Now, if you exclude the number 1, then you get rid of this, right? Okay, and then there are final regions that represent 0.001 something, 0.021 something, and 0.201 something, 0.221 something, right? These are also excluded. I mean, this helps you understand what the structure of this set is. All right, you are basically removing a digit, right, from a base 3 representation of all real numbers. You can also, from this representation, you can also see that this set and the set of all real numbers actually has a one-to-one mapping, right? So you can map all these. You can construct a map that takes a base 3 representation and convert all the digit of 2 into digit 1 and think about it as a base 2 representation. Then you can actually get all the whole real line from this Cantor set. So basically, that kind of is a proof that the Cantor set is uncountable, right? Because the whole the whole interval between 0 and 1 is uncountable. So the Cantor set is uncountable, and it has a measure 0, right? I mean, that's probably the simplest uncountable measure 0 sets you can construct, right? All right. Any questions on that? No? Okay. So let's look at how the dimension can change, right, as we increase or decrease the unstable and the stable directions. So, for example, the unstable direction. Let's imagine instead of instead of taking xm plus 1 is equal to 2xm mod, let's say, pi, right? What if we remove the 2 and make it m, like m multiple of x, again mod pi? All right. Okay, and ym plus 1, of course, I have to take this m times xn divided by, take the integer part of this, all right, and plus yn divided by a, where this a has to be greater or equal to m. So this is a stable part. I can also have a different a, right? So here, what I'm doing is I'm increasing or decreasing the rate of expansion in the unstable direction and the rate of contraction in the stable direction. So how does that change the dimension of the ergodic measure. So let's think about what this does. Now, if I make it m, instead of the y dimension being restricted from 0 to 2, right, it'll be restricted over a bigger space. And it'll be restricted between 0 and m. All right, because, well, if a is greater or equal to m, then if yn is less than m, right, this is going to be less than 1. Okay, and this is going to be less than m minus 1. So the whole thing is still less than m. Okay, so y is going to be always going to be in 0 to m. Now, think about what happens. So when you have the space between 0 and m, right, every time you contract the whole y-axis again by a factor of a, right? So here you contract it from 0 to m to 0 to m over a. But you're duplicating the structure not twice, but by m times. So you have one structure duplicated from 0 to m over a. You have another structure duplicated from 1 to 1 plus m over a, and then 2 to 2 plus m over a, etc., all the way to m minus 1 to m minus 1 plus m over a. Right? Now think about what this does to the dimension. Okay, so still we take epsilon being, let's say we start with the whole set, right? Epsilon goes from m, okay, and m over a squared, etc., m over a to the ith. So every time you decrease the size of the ball by a factor of a, you have to increase the number of covers, right? So we are going to start with 1, right? So if I have a size of m, I just need 1 interval to cover the whole thing. If my size is m over a, I need 1, 2, 3, etc. m balls to cover the whole thing, right? And when my size of a is even smaller, I'm mapping this whole interval from 0 to m with m separate little sets into this smaller domain. So I'm getting even like smaller, finer structures within this m duplicate copies. So I need m square small balls to cover the whole thing, etc. And at some point I would need m to the I balls to cover the whole thing, right? Does it make sense? Any questions on this? Yeah, so at the end, what is going to be the dimension? The dimension is going to be, let's take this again, right? The log of n divided by the log of epsilon minus, right? What we get is really log a log m. All right, that's going to be the dimension of the system.
Could you make that integer? And what does the Cantor set look like at that point?
Oh, yes. For example, if I make m exactly equal to a, what happens? Yes, if m is equal to a, we actually did an example last time, right? When I take m equal to a equal to 2, I mean m is always equal to 2 in these cases, I get the whole two-dimensional space. And of course, if I only look at the y direction, right, it's the whole interval, so I get a dimension of 1, right? And another thing is, if I think I took a that's very large, right? So if a is very large, the log of m over log of a is almost 0, right? So we got, well, pretty much 2 lines, right? And if you only look at the y direction, it's almost like just the 2 points, one at 0, one at 1. so that dimension is like 0. I mean, it's not going to be exactly 0 because if you really zoom in, you're going to see some structures. And then you have to zoom in a lot of times again to then see even further structures. So it's not going to be dimension 0, but almost dimension 0. All right. Okay. Yeah, good question.
What does it look like when it's a dimension of like tau, like not an irrational number like this now? Is it anything in particular interest? Anything interesting?
Nothing really special. So let's, for example, make a equal to 4, right? Let's actually let's make a equal to 4 and do it again. Let me actually just copy this whole thing and make a equal to 4 and run it. So we are going to make a second histogram. We have these both sides. N2, let's say N2 is equal to H2 dot this, and let's plot this and this, right? This finished. So we are N2 is going to be what happened? N1. Thought I kind of N actually was overwritten. Yeah, so you're going to see that. Yeah, so the blue line is the same as before, right? The log 2 over log 3 dimension, and the orange line is the N2 that has exactly a dimension of half. You can kind of see by measuring the slope here. And if you really plot it, like what we plotted here, it doesn't look really particularly different from previously. I mean, the only thing different is that the bins are exactly aligned with the because the bins are like a factor of 2, right? So they are exactly aligned in the sense that when you look at the whole interval, the middle half is going to be excluded, and then for the first quarter and last quarter, the middle half again is excluded, right? So basically the boundary of my histogram is actually exactly aligned with the boundary of the structures. That's why like it looks pretty much uniform. Like the non-zeros looks very uniform, but that's kind of an artifact. If I make the bins exactly aligned with 1/3 and 2/3 in this one, right? If instead of a power of 2, I make a power of 3. For this case, I would get actually exactly something that would look like that.
Okay.
Yeah.
Thanks.
Okay. So this is really just looking at the y dimension of the Baker's map. What do you think if I look at both x and y direction? Do you remember what the x direction looks like? It's contiguous, right? So what is the dimension of the two-dimensional Baker's map if you look at the x and the y, right? And think about what is the dimension of how many n's you need to cover the two-dimensional space. What do you think? Yes, it's just the +1. Let's think about from the definition of the dimension, right? Okay, so how many balls do you need to cover? So we know that you need a contiguous set of balls in the x-axis to cover, right? But in the y dimension, you are allowed to make some gaps, right? In the y dimension, there are gaps. So the total number of balls, the two-dimensional balls, has to be equal to my n1d, the number of one-dimensional balls or one-dimensional intervals I need to cover the y-axis, times 1 over epsilon, right? Okay, so my log of n2d over minus log of epsilon is going to be equal to log of n1d, right, plus the log of 1 over epsilon, which is minus log of epsilon divided minus log epsilon, which is going to be exactly log of n1d divided minus log epsilon plus 1. Okay, so whenever I supplement a fractal dimension with another dimension, a new dimension that's continuous, okay, I'm increasing the dimension by 1. So if you look at the whole Baker's map, for example, of our when m is equal to 2, a is equal to 1, a is equal to 3, right? So we have a dimension of log 2 over log 3. The whole Baker's map is going to have a dimension of log 2 over log 3 plus 1. And what does it look like? It looks like this, right? So this is generating this plot. I don't think it took too long, maybe just 4 or 5 minutes of rounding with the GPU, right? So you're going to get if you count the density of points, lies with, I mean, this is a mapping. I scaled the mapping from 0 to 2 pi to make it in both dimensions. But like if you really look at the two-dimensional histogram, you get this structure. Okay, so this is really what a 1 plus something like 1.6 something dimensional object look like. All right. Okay. Let's see what's next. So this is the okay. So what is the general formula for the dimension of a chaotic map? So the general dimension is quite interesting. So first of all, for all the unstable directions, so a chaotic map, right, in this case only has one unstable direction, but all the unstable directions are going to have continuous all the unstable directions, they are going to have continuous measures, right, in their respective directions. So if you look at the Lyapunov exponents, the first Lyapunov exponent is always going to be positive, right, and etc., and then you starting from some point, the Lyapunov exponent starts from going from positive to negative. Okay, then the dimension of the whole attractor, you first have to add the number of unstable directions, because these directions are like the x direction of the Baker's map. They are just going to be continuous directions. So you first add the number 4 into the picture. Okay, and then what happens is that each stable direction is going to be like what we have over here. It's in the Baker's map. It offers a contraction that counteracts with the expansion of the unstable directions. So and up to what point? Up to the point that the summation of the Lyapunov exponents are going to be exactly equal to 0. Okay, so if I have a particular I goes from 1 to n, if I have an integer number of Lyapunov exponents, the sum of which is equal to 0, then that number is going to be the dimension of the attractor. So that's a special case, right? Just to think about then n is dimensional, n dimension is the dimension of the ergodic measure. So the way to understand this or give an example is our previous case where a is equal to 2 and m is equal to 2, right? So in this case, we have a unstable Lyapunov exponent that is a log of 2, and we have a stable one that's minus log of 2. Okay, the sum of the first two exponents are exactly equal to 0, and we get a two-dimensional attractor, right? Remember, like in our first case, we get a ergodic measure that covers the whole two-dimensional space. We have a 2D measure. But most often the case, we cannot have an integer number of exponents, right? Contraction and expansion rates that sums up to exactly 0. We usually get a point where the summation of I to n lambda I is still greater than 0, but if you add up to n plus 1, you get less than 0, right? So that's the case we have for example, m equal to 2, a equal to 3, right? So then the dimension of the system actually is going to be in between n and n plus 4. Okay, so again, like in our previous case where the first Lyapunov exponent is positive, but the second Lyapunov exponent is more negative, right, than enough to counteract the first exponent. Then the dimension is going to be between n and n plus 1. And what exactly is going to be the dimension? It actually is exactly okay. So we let's denote this as a, right, and denote this as minus b. Okay, one is positive, one is negative. Then the dimension is going to be n plus essentially what is the weighted average of these two sums that would make the weighted average actually exactly 0. So the sum would be a over a plus b. All right. So essentially, what happens is that if this sum is very close to 0, and if you add one more Lyapunov exponent, it's going to be way negative, and then the dimension is going to be closer to n, right? If a is much smaller than a plus b, right? B is large while a is small, then the dimension is closer to n. On the other hand, if b is small, a is large, right? Then the dimension is closer to this, right? It's going to be closer to n plus 1. Okay, and the special case is when n is equal to 1, of course, in our previous case, right? Then if n is equal to 1, it is going to be 1. If n is equal to 1, basically then what happens is that lambda a is going to be the first exponent, right? B is going to be B is going to be the first plus the second. Yeah. The B is going to be the negative of the sum of the first two exponents, right? So what is A plus B? A plus B is going to be the negative of the second exponent, right? So in our case, in our special case, right, when n is equal to 1, my A is going to be the log of m, right, which is the first exponent. B is going to be minus log m plus log a, right? It's the negative of the first exponent minus the second exponent, and therefore this is equal to 1 plus log m over a plus b, which is going to be log a. So this is exactly what we derived for the Baker's map. All right. Okay, so we'll think about this fractal structure of the attractor later on when we start to look at the long-time average quantities of a chaotic system, which is really an average weighted by this ergodic measure, right? Okay, so we'll think about that later.
I just have a quick question about the last equation. Is it, like, can you prove that this is true for any fractal object? It seems more so like you kind of pulled it out and it's coincidental that it works with the Baker's.
Yeah, so you can prove it for maps that are uniformly expanding in the unstable direction and uniformly contracting in the stable direction. Okay, it's so that's almost easy to prove, and there are more proofs when the expansion and the contraction are not exactly uniform, but still uniform enough. But you can't really prove it in general, and in fact, the dimension as we defined is called the box counting dimension, and there is another name for this particular dimension, and the proof is basically these two dimensions are exactly the same for like uniformly hyperbolic systems or nearly uniformly hyperbolic systems. By hyperbolic systems, we'll give the definition later, but it's really the systems where the expanding directions are uniformly expanding, the contracting directions are uniformly contracting.
The definition makes me think, some chaotic systems are also intermittent, which would be uniform, right?
Exactly. Yes.
Okay.
Yes. For the intermittent systems, you can't prove it in general that these two dimensions are exactly the same.
Okay.
Yeah. Mm-hmm. Okay. Another important, another interesting fact about the Sawtooth and Baker's map is about the dynamic entropy. Okay, so what is the entropy of a dynamical system? So the entropy about the dynamical system has a very it has a definition that is quite similar to what we have for the dimension, right? But that's actually a little bit different. So the entropy is a measure of the diversity of possible trajectories. So let's imagine you have a trajectory, right? So you have xy1, you have xy2. Let's just focus on the Sawtooth map for now. You have x1, x2, etc. to xn. Okay, you have a trajectory like this. So how does the diversity of the trajectories increase as you look at longer and longer trajectories? Well, first of all, if you look at the trajectory of length 0, right, you only have one possible trajectory. That's a trajectory of length 0. It's trivial. Then, when you look at the trajectory of length 1, just look at the single point. Okay, you can have for the Sawtooth map, you can have the trajectory is the point, and you can have any point in the real axis, right? So how do you define the diversity? You define the diversity again, just like the box counting measure, by dividing the whole space into segments, right, of length epsilon. So you are dividing the trajectory, dividing the whole space between, let's say, 0 and pi into space of epsilon, and look at how many possible so basically the number of possible trajectories if this division is the precision of your observation, right, of the trajectory, then the number of length 1 is going to be pi over epsilon, right? So that's how many possible different trajectories you can observe if the precision of your observation is epsilon. Now think about a trajectory of length 2, right? Okay, if I have a completely random jump between one point and another, then the potential number of trajectories of length 2 is going to be pi over epsilon squared, right? So that's assuming I don't have any dynamics. I would just be the point of the solution would be randomly jumping from one point to another. Then I would have the square of that number, but that's not true, right? I do have a dynamics that constrains what my trajectory is going to be. So on the other extreme, if I have a non-chaotic map, for example, if xn plus 1 is equal to xn, right? So I have a exactly one-to-one map, or xn is equal to xn plus a, right, mod pi. So I have a like constant shift. Then what happens is that n2 would be exactly the same as n1. If I know where the trajectory is at the first step, I know exactly what the trajectory is going to be at the second step. There is no additional information, right, when I'm looking at a longer and longer trajectory. Looking at the one snapshot is enough for me to know what's going to happen in the infinite future. All right, so that's a non-chaotic map. But for a chaotic map, we get something in between a fully predictable system and a fully unpredictable system. And the degree for which I'm lying in between these two extremes is characterized by the dynamic entropy. All right, so that's actually what's happening here. So let's imagine what is N2. Yes?
So dynamic entropy is the number of patterns that we will see in the chaotic system.
Yeah, so the dynamic entropy is basically how unpredictable a system is. Right, so how much new information, it's more like an information theoretic measurement, right? So how much, as time goes on, what is the rate of new information I can observe from the time history of the system, right? So essentially, for a completely predictable system, there is no new information generated, right? So if I observe just a one-time snapshot or sufficiently many time snapshots, then like basically the future evolution is trivial, right? By keep observing the system, I don't gain any more information. But for a chaotic system, right, as I keep observing the trajectory, I actually gain more and more information. So that's the rate at which information is generated with a finite precision of observation is the dynamic entropy. Okay, so what is N2? If I look at two time snapshots, what is the possible, how many possible solutions do I get? So this is in 1D, right? So let's imagine I have two solutions, and I say this is x1, this is x2 for the sawtooth map. What is the possible space occupied, right, by possible trajectories? I know my map goes like that, right? So if you draw small epsilons, right, which and you draw also small epsilons also in the x2 direction, and count the number of boxes, how many more boxes do I have in this two-dimensional box counting compared to a one-dimensional box counting? Right? I mean, if I just count in the x1, right, I observe a simple trajectory of length 1, right? I can have like pi over epsilon many possible solutions. Now, if I observe 2 snapshots, right, trajectory of length 2, how many boxes would be possible? Not squared, right? Because I can't have a solution here, right? I can't have a solution here. The map actually is deterministic. I mean, squared would be what happens with a completely random system. Let's just make a very coarse box. So if I just split the whole space into 2 segments, right? If I just observe solution of length 1, I have 2 possible measurements. If I observe a solution of length 2, right, I have 4 possible measurements. But if I split into 4, then it's different, right? I cannot have any solution here, 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 or here, here. If x1 is over here, right, then x2 has to be either one of the 2 and cannot be one of these 2. So it's actually less than the squared. Exactly how many more, right? So if I split into 2, I have 4, right? If I split into 4, I have how many? I have 8, right? Half of the space is not allowed. If I split into 8, how many do you think I will have? 16, exactly, because yeah, this is actually a one-dimensional map, right? It occupies a 1D space. So because the slope is actually equal to 2, right? And 2 is actually going to be n1 times 2. And it turns out that n3 is going to be, again, it's going to be doubled, right? It's going to be 2 times n2, exactly, right? So every time the, let's see, actually, one second. Yeah, yes, right, okay. Yeah, so every time, really, if you look at the x1 versus x3, right, the slope of the line is going to be 4, right? So basically, for every iteration, you gain really just the 1 bit of additional information, right? So imagine like if x1 is again a binary representation with infinitely many bits, right? And imagine your observation precision is basically cut off over here. You have finitely many bits of observation, and for every iteration, 1 additional bit shifts into view, right? So basically, if you observe a trajectory of length n, you get basically you get n-1 times another bit shifts into view. So essentially, the additional information you can measure, right, is over time is going to be increased by like 1 bit per iteration. So this is what's going to be measured by the dynamic entropy. So the entropy of a trajectory is defined as the summation of, let's say, with the epsilon being the measurement precision, right, is the summation of pi log pi, where I goes from 1 to the number of boxes. So let's say the number of possible measurements you can have. All right, and in this particular case, all the PIs, if you split up equally, all the PIs are going to be exactly the same, right? Because we have a uniform measure. And the log PI would be, right, so basically all the PIs adds up to 1. So basically this is equal to the log of each individual probability that the system sits in one of them. So it's going to be a log of 1 over n. Okay. All right. And then the entropy of the dynamical system is going to be the limit with 2 limits. One is epsilon goes to 0. It's the inner limit, and then there is a limit of t goes to infinity of h epsilon over t. So that is, so first of all, taking epsilon goes to 0 means I'm having like a infinite, actually the other way, sorry. So I have to take the time goes to infinity first, because otherwise I would get, infinity. Right, so the taking time goes to 0 means I'm not going to be looking at how much information I have in a finite time trajectory, but I'm looking at how fast the information would be increasing, right, as time goes on. So, and then take epsilon goes to 0 means I'm looking at the rate of information increase for a sufficiently fine measurement precision. Okay, so in this particular case, no matter how fine you split the domain, what is the rate of information increase, right? So log of n, log of 1 over n would be, I think there is a minus sign on that. So right, so that is going to be the log of n. So the amount of information increase is going to be by a factor of 2 for every iteration. That means my entropy is increased by a constant additive value of log 2 for every iteration, right? So this is going to be equal to actually log 2, no matter how epsilon goes to small. All right.
Is it like 2 power of some, right?
Yeah, so n is going to be the 2 to the power of t, right, times the existing n1, right? So that is saying like log of n would be log of n1 plus t times log of 2. Okay, so let me just write it. This is log of n1 times 2 to the t, right? Which is going to be t times log 2 plus log of n1. If you take t goes to, if you divide this by t, right, the second part is not important anymore, and only the rate of increase as t increases would matter if you take t goes to infinity. That's why I'm saying if the purpose of taking t goes to infinity is looking at the rate of increase as opposed to how much information we have just by observing one snapshot, right? It's basically the rate of information being generated over more and more iterations. All right, that's why like for a non-chaotic system, even if you take a snapshot, you gain a lot of information, right? But then if you just observing the system for longer and longer, at some point you no longer get additional information anymore. So that's why the dynamic entropy of a non-chaotic system is 0. All right.
Is it possible to predict some other patterns from few snapshots of chaotic system? I mean, this limited amount of information of chaotic system does some information inside that tells us about the future's pattern or dimension.
Yeah, so this doesn't preclude that like you can predict the patterns even way in the future. So a lot of the patterns or recurrent patterns in chaotic system happens when you take a like zoomed out or like large granular point of view, right? Which in this case corresponds to a relatively large epsilon, right? So if you are able to, if you divide the phase space into larger segments, right, you can still, it doesn't preclude you from being able to predict well in advance what the large scale features of the system will be well into the future. But the dynamic entropy actually really takes epsilon goes to 0, right? So that is basically saying that in the fine scales, in the fine structures, how much more information is generated, right? So basically, if you can observe like if you have very good observation, right? That's really the definition. All right. Okay. Yeah. So maybe before we end, I'm going to just tell you what is the general formula for the dynamic entropy, right? So unlike in the previous case, we are looking at the summation of the Lyapunov exponents. Here, in this case, we are just looking at the Lyapunov exponents and essentially looking at the summation of the Lyapunov exponents until it reaches the 0 point. So if you are summing up all the Lyapunov exponents are equal to 0 and n until right, so essentially you are integrating or adding up the Lyapunov exponents until you reach 0. So essentially you can think about the integral, right, or the summation of the Lyapunov exponents, and that's going to give you the total dynamic entropy. Right? For a purely expanding system, it's easy to understand. If you have multiple directions where you are generating new information, right? The total new information generated per iteration is the sum of the lambdas. I mean, this log 2 is the Lyapunov exponent for the sawtooth map, right? So, and if you have expanding and contracting directions, the contracting directions also comes into view. So we'll look at in the next lecture, we'll look at not just the sawtooth map, but also the Baker's map and understand what is the role played by the stable direction in the dynamic entropy of the system. All right. Okay, so no lectures next week, and after spring break, we'll start to talk about the unstable directions role in the perturbation of the statistical quantities as you change the parameter of the system, right? And then after that, we'll really start to combine the unstable direction with the stable directions and the neutral directions and look at how a general chaotic dynamical system behaves on the perturbations in initial and the parameter values. All right, so see you, have a nice break. See you Monday after the break.